Welcome to Brain Vision.
Hi everyone. So what we have is steam that's passing through a throttle with a well-insulated valve. And what we're asked to solve for is the final temperature, knowing that the steam is coming into the throttle at an input pressure of 8 megapascals and at 350 degrees C. And we're asked to vary the exit pressure from 1 to 6 megapascals. So what we're going to do first is just write down our assumptions. So we're going to assume that this is a steady state problem, so nothing is going to be changing with time. We're also going to assume that any changes in kinetic energy or any changes in potential energy are negligible. We're also going to assume that heat transfer to the fluid is negligible because we do know that the valve is insulated. And we're also going to assume that there's no work involved as well. So what we're going to do is take a look at the inlet condition and see what that tells us. So with an inlet pressure equal to 8 MPa and a temperature equal to 350 degrees C, we can ascertain by looking up the thermodynamic tables that we have an incoming enthalpy equal to 2,988.1 kilojoules per kilogram. And by doing our energy balance, we can say that the energy coming in minus the energy leaving is equal to the change in energy of the system. However, we know that this is a steady state problem, so the change in energy of the system is going to be equal to 0. Therefore, we can say that E dot in is equal to E dot out. And what this means is this is going to mean that the M dot times H1 coming in is going to equal the M dot times the H2 coming out. M dots cancel out, so this means that the incoming and exiting enthalpies are the same, which means that H2 is also equal to 2,988.1 kilojoules. Now what we can do is actually just use these two quantities and our exit pressure to find our exit temperature. So we know our exit pressure is going to be varying between 1 and 6 MPa. And our exit enthalpy is 2,988.1 kilojoules per kilogram. Go ahead and fix these units. So having these two pieces of information, the pressure and the enthalpy, define the state of our exit. Therefore, we can actually go ahead and correspond this state back to a temperature. And by looking these up in the thermodynamic tables, that is exactly what we can do, and we can deduce our exit temperature. So this is what it looks like. On our x-axis, what we have is we're changing the exit pressure from 1 to 6 MPa. And on the y-axis, what we have is the exit temperature. And as you can see, as we increase our exit pressure, our exit temperature increases as well.